Hello lovely humans, Jen Foxbot here. In today's episode of Math Mondays, we are going to look at how to find the electric field for a continuous charge distribution. Basically, you can kind of think about it like if you spread charge over a shape, what does the electric field look like? Okay, well, why should we care? Well, if this is the equation for the electric field and you have more than a handful of charges, which you usually do, you're gonna need an easier formula than adding up every single charge, because I would do 3 and then I would be like, okay, is there a faster way to do this? Yes, there is. Integrals. Da da da. Yay. Calculus. Okay. So we'll start by looking at the general formulas for continuous charge distribution for different types of shapes in 1, 2, and 3 dimensions. And then we'll do an example problem which should help you apply these general situations to more specific situations. Okay, here we go. Cool. Okay, so as a refresher, this is the electric field definition for individual charges. And as a reminder, script R is the vector pointing from your source charge, Qi, to your test point, P. And so the really important thing to keep in mind here is that this changes. Okay, so plug that into your head, and we are going to write the continuous charge distribution for a general situation. So you have E of R 1 over 4 pi epsilon naught. Okay, so this is where the integral comes into place. But now we have to ask the question, what are we summing up over? Well, we're summing up over a bunch of teeny tiny charges. So in this case, we are going to be integrating over dq, or basically like an infinitesimal amount of charge. And so then the rest of this summation kind of comes along for the ride. So we have, well, I shouldn't say comes along for the ride. It's very, very important. The electric field is a function of position, so we definitely need to include this. So the tricky thing here is that script R and script R hat are not constant, so we cannot pull them out of the integral. The best way to deal with these is, well, to pull them out of the integral, you basically have to convert it into Cartesian coordinates, x, y, and z, but it may actually be easier to do the integral with these. Kind of depends on the situation. So we'll look at how to convert them into Cartesian in the example that we have. Okay, so basically what we need to do with this general formula is convert dq into the particular shape scenario that we have. So let's say we have a line and the line has a charge distribution lambda. So in this case, we're going to have a teeny tiny length of charge, dl prime. We're going to use a prime so that we can keep it distinct from our standard Cartesian dl, or well, the kind of standard dl that we've used before. This is a different one. So in this case, with the charge distribution lambda, which is a function of position, we will get a dq that is equal to lambda times r prime, or sorry, lambda of r prime, not times, but then it's times dl prime. Okay, so that is for a line. And just for funsies, remember that if our test point is out here, this is script r. Okay, cool. So that is for one dimension. What about for a surface? Okay, so in this case, we have a charge per unit area. We're going to use alpha. And again, it is position dependent. And so then in this case, dq is going to be equal to alpha of r prime times dA prime, where dA is a teeny tiny amount of area like that. And again, script R is pointing to our point P. Whoops, not R hat. That is script R. But it does have a direction of script r hat. Okay, cool. And then finally, we have a funky volume, because volumes come in lots of different shapes and sizes. And in this case, we're going to be looking at a chunk of volume. So I'll draw a teeny tiny cube, and we'll do little p out here, a little test point. This is script r, which is a vector that changes. And we'll call this, we'll say that our volume has a charge per unit volume of rho. That's kind of charge density. Hey, that kind of is making some sense here. So our charge density is going to depend on position. And so in this case, dq will become rho times d tau prime, where this is d tau prime. Yay! Okay, cool. So then we would just replace dq with the particular equation depending on the type of shape that we have. Cool. Okay, so what I'm going to do, we're going to do an example problem, but I first wanted to again reiterate script r hat, not constant, script r squared, not constant. Okay, cool. Pictures, very helpful. Draw pictures for yourself. Okay, cool. So now we are going to find the electric field of the length of wire of 2L at a distance Z. We're going to draw that a little bit lower. At a distance Z above the wire. I was going to erase it, and then I was like, no, this is fine. Placement on the chalkboard, very crucial. Okay, so why is it length 2L? Well, because in electrodynamics, when calculating the electric field, symmetry is your friend. And so if this is the z-axis, this is going to be the x-axis. So we're going to do minus L to L here. And so, well, that's also in the problem. Find the electric field at a distance z above the midpoint of a charge with uniform charge distribution lambda. Clutch, because that means that lambda is constant, which is very helpful. Okay, so we're going to write down the general equation. So we have the electric field equals 1 over 4 pi epsilon naught. And we are going to integrate over a line. So I'm going to put an L there. And we have, well, okay, we'll start with this. Script r, that's a vector. Well, we'll just do squared. Okay, and then script r hat dq. Okay, so in this case, dq is going to be equal to lambda, which may be a function of position, times dl prime. In this case, it's not, so it's just lambda times dl prime. And since the horizontal components of this line are going to cancel, meaning this is the same as this is just going to be equal to lambda times dx. Okay, that's pretty cool. So we can get rid of that, and we can put lambda in here. Notice, again, the symmetry of the line. Whoa, almost lost a chalk. So if we want to integrate over the total line, or from negative L to L, we could do that, and we would get just lambda, but we'll get the same result, and we can be a little bit lazier if we just go from 0 to L and multiply by 2. 0 to L. So those are the limits of our integral. Yeah! Okay, so what the heck do we do about this pesky r hat? What direction is that? Okay, well, this is our test point, P here. So if I start out here, if I am finding the charge at L, I'm finding the contribution to the electric field from the charge at L. We have to be very specific in our words sometimes. So this is script R. Okay, so that means that script R hat is this unit vector here. Cool, okay, so I'm gonna make that a little bigger so that we can more easily see the geometry of this situation. So this is script R hat, and I can say, okay, well this angle down from the z-axis, I'm gonna call theta. Cool, easy peasy. And then that basically lets me do a cool little geometry trick where I can say, oh, well, another way to write script R hat is cosine theta times z hat. Wait, how does that work? Okay, so if we take this and we zoom in, I have my script R hat here. I have theta here, and this is the z-axis. So my unit vector z, ooh, chocolate makes me need to sneeze sometimes, is this length here. And so with my right triangle, cosine of theta is adjacent over hypotenuse. So cosine of theta is r hat over z hat. Hey, very cool. So I can replace script r hat with just cosine z theta. That makes my life way easier. So we're gonna do that now. Cosine theta, z hat, and I have a dx out here. Okay, cool. But wait a second. I do not like this because that's a little funky. And script r hat changes. So let's get it into Cartesian coordinates. Well, okay, now we can just use the triangle here, and we know that the vector r, script r, equals, well, I'm going to write for funsies, z squared plus x squared. So that is the magnitude of our vector. I guess I don't need to add that. That's the magnitude of script r, and cosine theta, this angle is, well, the same as, hold on. I think it's the same as this angle. Yeah, okay. So cosine theta can also, it's the equivalent to say that cosine theta is the same as z over script r. Boom. Okay, we are well on our way. Okay, so this cosine theta is going to give us a z over script r. So this is going to be script r cubed, which becomes z squared plus x squared to the 3 halves. Okay, now we can do the integral. Yes! Okay, a lot of substitution, but now we can actually do this. Okay, so all these things on the top are constant, including z hat. Woohoo! We don't have to worry about z hat in the integral. Okay, so we're going to pull those out for now. 2 lambda z hat over 4 pi epsilon naught. And then the integral is over z squared plus x squared to the negative 3 halves. And if you've done it before, that's awesome. You'll be like, haha, I can pull that one out of my back pocket. And if you haven't done it before, you can look it up on Wolfram and Alpha. Yay, Wolfram Alpha. Lots of people have had to do this before. So usually I'm just like, someone else has figured this out. I'm just going to build on top of their work. Yay! And the integral ends up being, for this chunk here, is going to be x over z squared. That is real crooked. Let me fix that. Okay, we're going to try that again. It's going to be x over, still really crooked. Wow, okay. Okay, line. We're going to x over, I feel like I need to really overcompensate. X over z squared times z squared plus x squared to the 1 half, and this is going to run from 0 to L. The 0 part's going to cancel because of the x on top, and we are going to get I am going to well, okay, I can rewrite it. 2 lambda z we'll pull the z hat out here in 1 second. We're going to get L over z squared. Can y'all see that? Is that too low? No, that's okay. Over z squared plus L squared. Well, just root. Okay. Okay. Nope, that's supposed to be a parenthesis, not a straight line. In the z hat direction. Woo! We did it! Okay. Now we can simplify a little bit. This will cancel with that. And I am just going to write it up here. We're going to get the electric field. Wow, yeah! Okay, the electric field is 2 lambda L over z squared times square root of z squared plus L squared in the z hat direction. Boom! Okay, so what does this tell us? Well, number one, it depends on the charge distribution. Cool, that makes a lot of sense. It depends on the length of a wire. Cool, that makes a lot of sense. And it also depends on the distance that you are trying to find the electric field at. Okay, so let's do a little bit of, oh, and it's pointing in the z direction, which is actually kind of interesting, right? Because you have a length of wire that extends in the x direction, but like we said, the horizontal sections cancel, and so the electric field only points up. Pretty cool. Okay, so now we can do some math tricks to better understand what this equation is telling us. So let's ask what happens if we are very, very far away from the wire. Or in other words, what if our distance P is like way up there and it's much, much bigger than the length of the wire. So in this case, the electric field is going to equal this fun constant out front. And Z is going to completely overwhelm L in this square root. So we can, basically L is going to go to 0 and we're going to get the square root of Z squared, or just Z. And we are going to get, wait, why do I feel like I did something that I didn't mean to do? Whoopsies. I dragged along this when it should have been canceled. Okay. So yeah, okay. So then square root of Z squared is just going to be Z. On the top, we're going to have 2 lambda L over Z squared, Z times Z. And again, in the Z hat direction. Okay, this kind of looks a little familiar. So this is basically the electric field of a point charge, where Q is, whoa, okay, I tried to write a 2 and a lambda at the same time. I got so excited. 2 lambda L. Okay, this is really cool because basically what this says is that we can treat this shape, this line, as a point charge when we get very far away. And the amount of charge of the line makes sense, right? Because it's the length of a wire, 2L, times the charge spread throughout that shape. Woo! I like that. I love it when things are like, oh, okay, that actually kind of looks a little familiar, and it makes, intuitively, it makes sense. And then it's, divided by the distance that you are from the wire. Cool, so it kind of looks familiar. Okay, and then the other kind of fun thing that we can do is ask, well, what if we have a really, 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 really long wire? Like if the length of the wire goes to infinity. Ooh, fun. So then in that case, the electric field, and this, in the square root, I keep forgetting the name of this symbol. It's a square root. In the square root, if L is a very, 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 very large, it's going to overwhelm Z. So we can neglect that, ignore and neglect at the same time. And the square root of L squared is just L. So we're going to get a Z times an L on the bottom, and the L's will cancel. So now we have 4 pi epsilon naught, 2 lambda over Z. And this would be the electric field of an infinitely long wire. One of the interesting things is that it, well, at this point, it doesn't depend on the length of the wire. So boom, there you go. Whew, okay. That was a lot of math and a lot of physics and a lot of fun. I hope you had fun. So I hope that this kind of helps show you how you can translate different parts of the equation for the electric field using geometry. Geometry is your friend in these situations. So look for, draw pictures, look for symmetry, and figure out how you can rewrite this script R, because Cartesian coordinates will allow you to pull things out of the integral. Or at least, you know, when you are ready to replace it. Sometimes it can help to do the integral with the script R. Depends on the situation, but trust yourself, do some practice problems, and have some fun. Okay, let me know if you have any questions about this or other math topics, and we'll see you next time. Bye!